All right, I want to do one last example in this section, example 5.3.2. I want to consider the region enclosed by x equals minus y squared plus 2 and x equals minus y. I'm going to start by giving a sketch of the region. I'm going to label all curves and intersection points. All right, so let's find these intersection points. I need x to be equal to minus y squared plus 2 and to minus y. I'm going to send it all to the right side. I'm going to get y squared minus y minus 2. All right, and that factors with a 2 and a 1. And I need a minus. I'm going to put it here so that yep. And so on the right, I have y equals minus 1. On the right, I have y equals 2. If y equals minus 1, x, which is minus y, will be 1. And if it's minus 2, x, which is minus y, equals minus 2. All right, so let me put these two intersection points. I have x equals 1, y equals minus 1. So 1 minus 1. I have x equals minus 2 and y equals 2. All right, good. Now I need to figure out which curve is top bottom, which curve is right left. In fact, I'm just going to use right and left because my curves are described with y as a variable. So I'll do that first. We'll worry about top and bottom later. All right, so I need to plug in a value of y between minus 1 and 2. I like to be lazy here, and I'm going to plug in 0. All right, at 0, the first curve will give us 2. So at 0, the blue curve will give us 2. And at 0, the right curve will give us 0. So this means that this curve is going to be right between minus 1 and 2, and this one is going to be left. In fact, I mean, if you're a bit careful, you should see that this is a straight line because it's just x equals minus y. And then the other one is some sort of parabola. It doesn't really matter how you draw it as long as it stays. Ooh, nice. It's just a tiny bit off. Ah, they're improving. Very good. So here's our parabola and our straight line, and we get this region right here. For this region, I would use horizontal slicing, no questions asked. I would use horizontal slicing without any hesitation because my curves are given as x is a function of y, and on top of it, if I do use horizontal slicing, I'm going to get the same curve on the right and the same curve on the left for the entire region, and that means a single integral. All right, so this would be, I'm actually forcing you to do it, find the area of the region using horizontal slicing. This would be the best way because the curves are given as x as a function of y, plus we have a single integral. So both clues in this case tell you to take that method. All right, so let's set it up. For horizontal slicing, it's C to D, right minus left. Remember, C and D are the values of y because I have dy here, so y is my variable. Don't want to see any x's in the formulas or in the bounds. So bottom value of y is minus 1. Sorry. And top value of y is 2, and so d is 2. All right, so I have integral from -1 to 2. Right, we said, was the blue curve, so right is minus y squared plus 2. Left is the green curve, and so it's minus y. Right, so if you integrate it, you'll get minus y cubed over 3 plus 2y plus y squared on 2, in which you'll plug in minus 1 and 2. I actually computed it and got 9/2. And that's the area of the region. All right, you're thinking we're done. Perfect, we used the right method. But I want to show you why it's the right method. And the best way to do that is to use the wrong one too. All right, so in problem C, I'm going to ask you to find the area of the region by using vertical slices. All right, that's going to be a bigger challenge. So first step is I need to isolate y in each curve. So if I have, let's start with x equals minus y, I'm going to need to write this as y equals, well, I'll just send the minus to the other side, minus x. So that one wasn't so bad. So that's for the green. But now the blue one is going to be a bit of a challenge. Second one, I have x equals minus y squared plus 2. Yep. And so if I isolate y, I'm going to get x minus 2 is minus y squared. So y squared is minus x plus 2. And now I need to take a square root. So really, y will be plus or minus x plus 2. So the blue curve right here is going to turn into two different curves now. We're going to have this part, and we're going to have that part. All right, so we're going to have y equals square root of minus x plus 2, and we're going to have y equals minus square root of minus x plus 2. All right, so let's redraw the sketch with the three curves that we now have. Right, so we still have y equals minus x. That one is still the same. And we know that it intersected the blue curve at the point minus 2, 2, and the point 1, minus 1. So this will still be the intersection between this one and either of these. But now we are going to have an extra intersection point because these two different curves could actually meet, and they do meet. So I could have minus x plus 2 equals minus x plus 2. And so that would mean that 2 root of, minus x plus 2 is 0. So minus x plus 2. If I square, I get, so I'm getting x equals 2, and at x equals 2, my y is going to be 0. So I have a new intersection point at 2, 0. All right, let's use a bit of our information here. We already know what the general appearance is. So I'm going to use, let's use purple because it's close to the blue that we had. I have this part. And we knew that we had, let's use red, orange is good. Let's use this one as well. Right, so the curve is split into two. They meet at 2, 0. This one has a positive y, so that one is going to be right here. The one with a negative in front of the root will have negative y value, so it'll be lower right here. And then on this side, I have x equals minus y. Oh, sorry. That's true, but I want y equals minus x because I'm using vertical slicing now. Right, already you can see this is a bit confusing. Now I'm going to draw my vertical sticks, and you notice that at this point right here, bottom switches, and so I'll have to split my integral and compute two separate regions. All right, let's do it. Integral from a to b of top minus bottom. I can't really spell it out because bottom switches, so I'm going to just do parts of it. Minus 2 to 1. Top is orange, so root of minus x plus 2. Bottom is green, minus x. And then from 1 to 2. Now we're talking about this part of the region. So top is going to be this curve, and bottom will be this one. It will be the purple one. So here I have root of minus x plus 2 minus root of minus x plus 2. Sorry, I'm a bit short on room. Let me move everything slightly that way so I can just write my dx. All right, so I've computed both these integrals before. First one should give you 19 over 6. Second one is going to give you 4 over 3. And if you add it up, what do you get? Same. It's the same area, so you should get the same answer. So 9 over 2 either way. In this case, vertical slices is much more complicated. It's more complicated because you end up with more curves, you end up with more integrals. Every piece of this is more labored and more work intensive. This was so short, nice and sweet. Right? So if the curves are given as x is a function of y and you don't have a reason to change it, just leave them. Leave them. It's so much better. All right, so that's it for horizontal and vertical slicing. In the next video, we'll start looking at consumer and producer surpluses, and that's going to be our first application to econ. All right, see you then.